Please welcome co-hosts of the Acquired podcast, Ben Gilbert and David Rosenthal.
It's quite the video, right?
That is quite the video.
Yeah.
Well, welcome to Google Cloud Next.
Ooh. Should we do like a show intro? I'm Ben Gilbert.
I'm David Rosenthal.
And we are your hosts. And we are going to be having a great, very interesting conversation today. If the conversation backstage is any indication, you guys are in for a real treat. For those who don't know, the Acquired podcast is a super long-form history of tech and other companies that David and I do. Last year, we did a 3-part, 10, 12-hour series on the entire history of Google, from the origin of search to this AI moment that we are in now. And when Google called and said, well, do you want to interview Amin and Jeff on stage? It was kind of a no-brainer. Yeah. So excited to do that with you here today.
Share it with you all. And with that, please welcome to the stage Google's SVP and Chief Technologist for AI and Infrastructure, Amin Vahdat, and Google's Chief Scientist and Technical Lead for Gemini, Jeff Dean.
Great to see you.
Great seeing you. Great seeing you.
Jeff, great to see you.
See you.
Amin, congratulations on your new babies.
These are beautiful.
Twins.
Beauty is an eye of the beholder, but I have to tell you, these are beautiful chips.
They are beautiful. This one looks a little bigger than that one. Is that right?
8T, this is our training powerhouse, and this is 8I. It is a little physically bigger, but actually the way that it winds up is there is actually more compute here. There's more SRAM here. Yeah. Mm-hmm. Yeah. So then that's part of the reason why we have inference, super low latency. We can hold things like the KV cache and other aspects all on the chip. Transfers between HBM and the SRAM is super fast. This one is built for throughput, raw horsepower at scale, goes up to 9,600 TPUs per pod. And then through our data center network and our software, actually, and if you heard it this morning, 1 million chips can work together thanks to Pathways and JAX. Jeff played a significant role in developing both of those, really act as one computer. In other words, you can write a single piece of code, and the compiler figures out, and the runtime figures out how to distribute it across all up to 1 million TPUs.
Yeah, even a single Python process is driving that whole thing.
Yeah,
it's like, this is the most googly thing I've ever heard.
Yeah, we got to ask. We thought to start, Jeff, we'd ask you, when you joined this small little, startup search engine that nobody thought was going to succeed
in 1999.
Yeah,
is that right?
Employee 30.
Yep, we were all wedged above what's now a T-Mobile store in downtown Palo Alto.
It always is bizarre going by it. It's like it's like a cell phone shop now. Yeah. But, did you think that someday you would be designing cutting edge silicon?
Well, I certainly didn't, because I had no experience in doing so. Yeah, but I mean, I think Google has always been a company with pretty large ambitions in terms of like what we're trying to set out to do. I like our timeless mission of organizing the world's information. I think that's like still what we're trying to do, and it has led to lots of interesting technical challenges that are still not solved over the years. So.
Well. Speaking of that, we thought we would start today to go back a little over a decade to 2013 to the beginning of the TPU project and the coming technical challenge that you and Google saw that led to this crazy idea that you would develop your own chip. Could you give us a little bit, take us back to that moment? How did the whole TPU program start?
It's a great story.
Yeah, so a little bit earlier than that, even in 2011 and 2012, we were starting to use very large numbers of CPU machines to train progressively larger and larger neural networks, because we had seen that every time we made, scaled up the size of the model we were trying to train, trained it on more data, we had a saying, bigger model, more data, better results. And that was true in numerous problems that we've tried in like the speech recognition domain, in lots of different kinds of vision tasks, and in language tasks and translation tasks in 2012, early 2013.
And this went on to kind of be colloquially known as scaling laws.
Yeah, so we never actually formally characterized that. We just had a around the micro kitchen, like, oh, we made the model twice as big and it's better kind of thing. But that really was something we were seeing in sort of progressively larger experiments over 2012 and early 2013. And so we had, in speech in particular, we'd managed to get the word error rate to drop as much from training a larger model in the last few months as the previous 20 years of speech recognition research had improved things. And so at that time, the existing speech systems just still didn't work quite well enough for people to really want to use them, because every fifth word or something would be an error. So it's like kind of frustrating to dictate something and then go back and fix every fifth word.
And we're like 5 years into the mobile era at this point, sort of smartphones.
Yeah, so in particular, the phones didn't have enough horsepower to run the speech recognition on device, so you would end up sending it to the cloud and doing recognition there. And so, but if we have the error rate, like clearly people are going to start using it more. So I just did a thought experiment as normally you'd say back of the envelope, back of a slide deck calculation, where I said, okay, suppose 100 million people start talking to their phone for 3 minutes a day. How much compute would we need for that for the best quality model we'd like to launch? And it turns out we would need to have a little bit more than twice as many computers as Google currently had to launch this new speech recognition feature. And that seemed like a lot.
For one feature. You need to
for one feature, yeah. It's like
entire infrastructure.
Better speech recognition, we would need the entire Google infrastructure again. And so that kind of scratched my head. I'm like, that doesn't seem really that good. But it turns out that neural network inference has this incredible property that it's very tolerant of reduced precision. And it's a collection of linear algebra primitives, matrix multiplies, vector operations, kind of strung together in different ways for different kinds of models. And so if you can build a chip that is essentially an incredibly good low precision linear algebra machine, which is what a TPU is, then you have a hope of having much better performance. And we published a paper in 2017 about the TPU v1 that originated from that back of the slide deck experiment, showing that it was 30 to 80 times more efficient than CPUs and GPUs of the day and 15 to 30 times lower latency. And so that was the initial TPU story.
And so the logic was, if we are going to do things like this speech to text and other things, we're going to need an ASIC, a custom piece of silicon that we make specifically to handle operations like that.
Yeah, so in the design process, we kind of had a few different kinds of problems we were trying to tackle. We had speech recognition, which had one particular class of model. We had various kinds of convolutional neural network models for vision tasks of various kinds. And then at the last minute, we started to say, oh, these LSTM things are interesting. Let's make the support, let's add in a little bit of extra support, even though we've already started designing the chip to support those. And that was how we were able to support Google Translate and a bunch of other kind of LSTM-like uses.
LSTM was the precursor to transformers.
Yeah,
invented
long short-term memory recurrent models.
Yeah. Wow. So how, I mean, we spoke with you a little bit about this last night, but to talk about it again here, most companies at this point faced with this problem, even other large technology companies with lots of resources, would have gone to, I don't know, Intel or Broadcom or NVIDIA and said, hey, make me a chip. That's not what Google did.
I think I'll tell a story. It's an apocryphal story. It was before I got to Google. Jeff, you were there. Maybe you can verify this. It's actually been verified where early on we realized to support some of the systems that Jeff and others had built in the early days of Google, MapReduce, Google File System, et cetera. We realized that we wanted a 10,000 port, 1 gigabit per second, which was a lot back in 2003, 10,000 port, 1 gigabit per second non-blocking Ethernet switch. That's what we wanted. So we actually then put out...
Which doesn't exist.
Which did not exist.
I'm just trying to imagine 10,000 ports on one.
So maybe it'd be, however the people wanted to build it, that's what we wanted. And back then it was like 100 megabits per second and you'd be lucky to get 32 ports or something like that. So we actually did an RFQ, a request for quotes, and we put it out there. And all the networking companies, everyone laughed at us. Every single one said, this is a joke, you can't do it, 10,000 ports, no way. This is what you want. And they came back to us with their 100 megabit per second thing, et cetera. So Google, being Google, said, we're going to just do it ourselves. Networking, how hard could it be? So we built this first system, and we actually built it as a PCI card because we thought network boxes, that didn't make sense. We know about servers. We're going to build a PCI card and stick it into the servers. The first one literally caught fire. Turned out building hardware was hard. It failed. But no, we didn't quit. We built a second one. And the second one actually went into production. I think at this point I can say it wasn't very good. People hated it, actually. They used it, but they wanted to avoid those servers. The third one was that non-blocking, by then, 10 gigabit per second, 10,000 port switch. It wasn't one box. It was hundreds of them, arranged in a rearrangeably non-blocking topology called the CLO topology. And it took off all across Google. It changed Google.
Absolutely, yeah.
Right? And I think it was lessons like that we were willing to invest in something that seemed crazy, that all the conventional wisdom, like everybody who knew anything about networking said, this is ridiculous. Why would you do this? We were willing to step up and say, we're going to try. We were willing to fail the first time miserably with fire, right? Like fire, smoke, right? The second time, it was an okay product, but kept going, and the third time, the fourth time, and Virgo, which we announced today, the million TPU network, it is a logical continuation of that third iteration. Right? And I had the privilege of working on the fourth version, actually, as my starter project at Google in 2010. And we were willing to, and so I didn't have to deal with the fire, but I got the benefits of the fire. But I think it's somewhat similar, because if you go back to 2013 and you said, what's the conventional wisdom for building accelerators? No, you don't build accelerators. You don't build ASICs for individual workloads, because they're going to get outdated really quick. By the time you launch it, the world will have passed you by. I think we probably could have gone, and maybe we even did go to NVIDIA, I can't remember, and others, I don't want to name one company, and said, hey, would you be able to build something specific for this? And probably were told, okay, it's going to take this amount of time, et cetera. We put out the first version, now different than our networking, the first version worked.
Of TPU v1.
V1,
Yep.
it worked,
Yep.
and it worked well.
Quick, like 18 months?
15 months, I think, from idea to deployment.
Yeah, really, really amazing.
And
Oh, we also speculatively bought a bunch of them without knowing how we would use them.
And use them all up?
Yeah,
Use them all up.
I accosted Patrick Pichette at the time, who was our CFO, and I said, we should buy a lot of these. And he's like, how many? I'm like, a lot.
well, it's one of these things where it's like, look, if we have all these Google engineers, we probably should give them something fun to play with and see what new products they come up with. And there were, even before the, call it 2021, 2022-ish, real explosion of AI that we're in now, there was a lot of narrow applications of machine learning that was really shining in Google products.
Yep. I mean, I'll give you an example. Like, this wasn't a Google product, but the AlphaGo match against Lee Sedol used 2 racks of TPU v1 chips for inference. I actually went and put a commemorative Go board on the side of that rack when I visited the data center. And that was a big factor in how we were able to do so much exploration of the move space by having lots and lots of parallel specialized ASICs. Poor Lee Sedol didn't realize.
We didn't talk about this before, but I'm recalling something from our episode research. Is it true that TPU v1s fit in hard drive bays?
They were PCIe-based cards, so you just slide them into PCI slots.
I always thought that was a very clever way of saying, okay, there's a lot of stuff we don't want to do. We want to focus just on this very narrow problem that we want to solve, and can we just fit it into existing hardware?
Yeah, I mean, I think the fact that we were trying to fit models that would fit on a single card made it easier, because you don't actually need that much bandwidth to go into the card or come out. Yeah. Whereas if you're trying to fit much larger models now, they don't fit on a single chip, even for inference, and you need much more complicated networks like we have for the V8i or subsequent TPU generations.
And it was really this TPU v2, which came out a few years later, that took 256 of these slightly beefed up v1s and connected them in a network topology. And the realization there is that we could use them for training these big models as opposed to just serving them.
Yeah. And again, with reduced precision. That was a big
insight.
Thing, yeah.
Yeah, for the less technical of us in the room, Jeff, I've heard you give explanations of this before, and I'd love to hear it. When you say reduced precision, why is that good? It sounds bad to me.
Because, so the reason you want to do this is think about multiplying a fraction with 6 decimal places times another number with 6 decimal places. That's super hard for you, right? Well, it's super hard for computers too. So if you can multiply numbers with 1 digit after the decimal place instead of 6, you just can multiply way more numbers with simpler multiplier units and do more of them in parallel. So you essentially can put many more multipliers into the same amount of chip area, and that gives you much more throughput, can reduce latency substantially, reduces the amount of data you need to move from memory and back out to memory when you compute results. So this is just, the cat's meow for deep learning and computer architecture.
My way that I characterize this is if you think back maybe to high school physics or maybe college physics classes, and when the professor or teacher was working the problems out on the board, they drive all these approximations. Like this used to drive me nuts because I was all about precision, but the professor would say 3 pi, let's call that 10. It's like, no, it's 9.42, blah, 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 blah. No, it's 10. And then these numbers, the ups and downs would cancel out, and then he'd come up or she'd come up with an answer that was remarkably close to the real one by just approximating everything through. So less precision is good when you can do it in your head and get almost the same answer with, let's say, 1/100th the work.
And it seems like there would be a trade-off where that affects the downstream model training, where, hey, let's make a good model that uses lots of precision. I always find it remarkable that the amazing frontier models that we have today are trained on the smallest possible precision hardware.
Yeah, I mean, I think one way to think about it is you have a bunch of different weights in the model, right? And if you reduce the precision of those weights, if you reduce it a little bit, it doesn't matter that much. If you reduce it a lot, then you'll lose some quality, but you can recover some of that quality by adding, say, 20% more weights, even though you have the number of bits in the precision.
More data.
So then, that's a good trade-off because it makes your model a little bit bigger in terms of number of parameters, but smaller in terms of number of bits you need to manipulate.
So this brings up a great point, and one we covered extensively in our series in Google. You were really unique in that you have a leading edge silicon accelerator operation, construction business, if you will.
You guys make TPUs.
You make TPUs, yes, that's the right way to put it. And that is married with a frontier lab, all under the same roof. When did that collaboration start getting really tight? I mean, obviously the frontier lab didn't quite exist yet in today's conception when TPUs started, but today.
Well, I mean, I would say the early work on large-scale training of neural networks actually informed the V1. So in some sense, we've been doing this for quite a while.
From the beginning, and Jeff ran Google Research, which did much of the precursor work here and ongoing still as well for many years. And his involvement with the TPU program has been deep, not just with V1. I mean, we talked about the slide deck, which was remarkable foresight. But I mean, Jeff has been deeply involved, V1, V2, V3, the architecture, the details, and bringing all the knowledge from the research and where things are going into every single generation of TPUs, including the 2 that we see here today.
I mean, the YouTube cat paper was TPUs, right? Was that still TPU V1, or was that
No,
later?
that was even pre-TPU. So that was in 2012. That was when we were trying to scale up large neural networks. And so we had some ideas around unsupervised learning objectives for images. So we said, well, let's just take 10 million random YouTube frames and see what the model learns from that. And so we trained a neural network on, 16,000 CPU cores using 2,000 different machines. And it turns out we trained a multi-layer model. And you could look at, after you trained it, what kinds of images did different neurons in that top layer get excited by? And it turns out, since we trained it on 10 million random YouTube videos, one of the neurons got very excited when it saw a cat face, because there's a lot of cats in YouTube. And other ones would get excited by kind of like pieces of cars or things like that. And that was completely unsupervised. We never told the model this is a cat or this is a car or a person. But because we trained a model 50 times bigger than anyone else had ever tried, the model had started to develop those kinds of representations purely unsupervised. And I think that was part of our bigger model, more data kind of revelation that we had internally.
I'm going to sidetrack, because I think this is an interesting conversation. What has that research developed into today? Trying to stare at specific neurons and saying, is this a cat neuron? Is this more abstract concepts?
We had a raging debate at Google in terms of whether we should be using these deep models for search. Jeff knows as well, because a challenge we had with these models was many times, maybe most of the time, they outperformed the sort of human-tuned algorithm, right? Like the algorithm that you could read and understand, oh, I understand what this algorithm is trying to do, and here's the search results. The model would outperform it, but here's the problem. You couldn't explain why. Like, why did this neuron become the cat neuron? And this other neuron become, so if there's a bug, how do you debug it? I think that continues today. I mean, Jeff, you can probably say more about this.
Yeah, I mean, I think unsupervised learning has taken a little bit of a backseat to what I would call self-supervised learning now, because what you do for training the most capable language models these days is you just take lots of text and then you hide parts of it for the model and you make it guess what's missing. And typically you make it guess, you get to see a prefix of the document, like the first part of a sentence, and then you have to guess the next word. That's literally the entire training objective for language models that are like having all these amazing capabilities today. There's other variants where you can take a piece of text and you can hide like 10% of the words. And then the model gets to look both left and right when trying to fill in the blank. That's a bit more like Mad Libs, if you might have played that as a kid. But that's not super great for conversational use, because you don't get to see the subsequent part of the conversation until you've actually had it. But that has also some good uses for like representing document summaries and that kind of thing.
All right, I want to zoom in on a concept that David is bringing up. You've got the TPU team over here. You've got Google DeepMind here. Can you tell us about the interactions? Like if I were to parachute into some meetings, how does it look? Who's bringing what to the table? What are each team sort of asking for? How much flexibility is there?
There's a lot of
a day in your life, basically.
Yeah, there's a lot of flexibility, and I think that the beautiful thing here is, and the goal is the same: build the best models, right, as possible, the most efficient models possible. So I think there's just a lot of give and take. So for example, the research team might have 7 different directions that look really, really promising, and they actually have more than 7. Hardware team has 7 different directions that look really, really promising. Now, how do you mesh those two? Right? And then there's a bunch of give and take, because what they'll settle on is, well, what if you change one of your 7 ideas in this direction for your model, and what if I change one of my 7 ideas on the hardware? Like, we can't do exactly what you want. That usually happens. Like the research team will come to the hardware team and say, we want X. And the hardware team says that's impossible. Now, if you're at separate companies, you just stop. Okay, bye, we'll maybe talk to another hardware person. You said no to our RFQ. So
we'd like a 10,000 port switch.
Yeah, exactly. Goodbye. On the flip side, in many other cases, the hardware team would come to the research team and say, we've got this awesome new widget. What would you like to do with it? And the research team would say, nothing. That sounds useless. I'm sure that your hardware widget is cool, but we don't want it. So it's that give and take that says, well, what if I took your hardware widget and I could do something different with my model? So that spirit of give and take is there really every single day. And this exploration of the joint space. It's not my space, your space. It's the joint space. And how do we build a system that can deliver the models, serving, training, agents, everything that can be as efficient as possible. That happens at all levels. Now, there's a lot of people at Google, so a lot of this is sort of engineer to engineer, which is exactly how you want it. And then some number of those ideas bubble up. Right?
Yeah, I would add, like, it's super hard as a hardware designer in an extremely fast-moving field like AI and ML, because you're basically, if you think about starting a chip today, it might sort of be done designing in 2 years and out in your data center, and then take, it needs to last 3 to 6 years or something. So you're trying to predict where is this incredibly fast-moving field going in the 2 to 6 to 8 year time horizon. And like 6 months ago, we just completely changed like lots of aspects of ML with some new algorithm. So that's super hard. So it's really good to have the insights of, researchers who are really trying ideas at small scale that seem like they might want to work. Like, the best thing for a researcher is an idea that just seems to want to work, because you know that you're going to be able to make it work with more effort, whereas ideas that kind of really don't want to work and you've tried everything, and those are probably ones that are less exciting. But I think that give and take and co-design is really important. I'll give you an example from the V8i, actually. One of the things we wanted to do was do very long traces for reinforcement learning, where you decode lots and lots of tokens, and like you generate, some, 500-line piece of code, and then you want to be able to run it and see if the code runs and passes the unit tests, and then get a reward for reinforcement learning. Well, in order to decode those tokens, you have to, do whatever the latency is for each token generation, for 60,000 tokens of generation. And if that takes a long time, then your reinforcement learning will take a lot longer, because it's not as low latency as it could be. And so the research team came to the TPU hardware team and said, we really need a way to make much lower latency, because it'll improve both online inference, but also reinforcement learning.
Yeah.
And so then people kind of put their heads together and said, hey, we actually could do relatively small changes to the chip that's being designed, but change the topology of the network. And that would actually not be a super dramatic change, but it would really help the latency for decoding.
This is the board fly topology.
The board fly topology.
Today.
So, I think that's a really crisp, concrete example of the kind of co-design that happens.
For years, we'd built these TPUs for throughput. And the inference example that Jeff was talking about, we would manage the latency by basically pipelining many, many queries, if you will, together. So we would do lots of queries. But for reinforcement learning, you can't pipeline many queries. This is the one. You're trying to generate this 500 lines of code, to Jeff's nice example, run it, and then test it, you get the results. You can't do the pipelining. So the throughput optimized engine, which AT continues, because, by the way, for other use cases, you still need that massive throughput, wasn't the best fit for this latency, okay, let me get a single result out case. And the hardware team would have naturally been inclined to say, let me just make the last thing faster. That's good.
Yep.
But it completely misses the use case of the coming research problem. And without having that tight conversation, you're going to miss that.
So the future is not known, the future is fuzzy, and every incremental day that you get out in the future gets less and less clear. You've got all these world-class researchers who are developing, what's the next transformer, what's the next, and there's a huge gradient of confidence that you have in the next iteration. How do you allocate bets when you only have a fixed amount of space in silicon, and then that thing needs to live for 2 to 8 years?
This is the raging debate every single day.
That's the whole process of co-design.
Every single day.
Right?
Yeah, you got these probably like thousands of ideas, and you can't put them all into silicon. They're all, as you said, it's a probability distribution function looking out 2 or 3 years. And you got to pick the 4 per generation or whatever. Maybe it's 5. But it's not 1,000. You get 4 or 5 things that you get to put in that's big and risky and bold. Okay, so now how do you project out into the future? You write simulators, actually. So in other words, it's not that we're completely saying, okay, I like this guy, I don't like this person, so I'm going to go read, then actually run bake-offs.
Yeah.
And having high fidelity simulators is really, really important. You have to make predictions about the workload. many, many variables. The simulators aren't, in the end, they'll winnow out probably 90% of the 1,000. Maybe even 95.
Wow.
Which is good.
Yeah.
But now you've still got 50.
Right, and then it's a judgment call of like, how important do we think this thing will be 3 years from now versus this other thing 5 years from now or 2 years from now?
And I'm sure you're looking for clever ways of saying, like, can we kind of accomplish both with some unique, I don't know, multipliers or something on here?
Yeah.
Yes, exactly. We're trying to get as much in as possible, but there's only going to be room for so much. Inevitably, there's going to be some folks who are slightly disappointed, but I think the nice thing about all being on the same team and all having the same goal is everyone's in the process. Everyone actually, the other important thing about Google is a sense of, and I think reality, that it's a open, data-driven process. There's no perfect decisions, and the people make the best decision they can together. And then there's trust in, okay, this is the call we made, now we're going to go execute to it. And maybe there's another train coming in 12 months, probably. We talked about that. Maybe there's 2 trains coming in 12 months, who knows?
Yeah, how often are the trains?
Right.
Lay this out for us.
And so maybe I didn't get on the train this time, but I contributed to the understanding.
Yeah.
And maybe I get on the next train.
Are you
TPU v9 can have that, yeah.
Are you doing new silicon every year now? Is that
The data seems to suggest that we're going to be doing silicon every year. Yeah.
This is 1 year, and there's 2.
Yeah.
Yeah, there's 2. So we've been talking about this incredible interplay within Google, between research and hardware and the TPU team. There's a third dimension too these days, right? That wasn't there in the beginning of the TPU project, which is, I'm sure there are a lot of Googlers in the room. There are probably a lot of non-Googlers in the room who use TPUs now.
I hope so.
Is the third parties. How does that play in the mix? Or maybe actually first, talk us through the decision to expose TPUs in Google Cloud to third parties. I can't imagine that was, I imagine that was a complicated decision.
It wasn't. It wasn't. It was, I mean, we announced them in 2018. Jeff, from day 0, I think, that's fair to say, has been a big proponent of making TPUs available externally to people, from academics to other companies. Sundar announced the first cloud TPU in 2018. I think we probably made the decision in 2017. So this was around V3 or so, where we didn't want to announce V1. I mean, Jeff knew it was going to work. Many others knew it was going to work, but it still hadn't been proven. V2 was our first training. So by V3, oh my gosh, this thing is real. Other people can take advantage of it too.
And I think we saw a growing use of machine learning in the world. Right? Like Google was kind of on the earlier side of adoption of that, but we saw many, many different companies and institutions realizing that this approach could solve problems they cared about.
And at the same time, though, I'm sure there was more than enough demand within Google to soak up every incremental TPU that
and still is.
It still is that you could produce. Like,
so I think there, of course, that becomes a variant of the how do you get your ideas into the TPUs, and it's a portfolio. I think it's a portfolio. In other words, we are incredibly fortunate where we have a cloud, we have the world-leading research lab, and we have services. In other words, we've got the distribution channel. We have 12 services with more than 500 million users each, daily users each, and all of them are using TPUs. Okay, so now you have some finite amount of TPUs. How do you allocate among them?
One thing I would say has helped in the past few years is we've sort of, like before Gemini, we had lots of different kinds of models being used by different teams for this or that. We had like convolutional models for vision things. We had lots of recommendation kinds of things, some ad prediction things. And those were all a bit distinct. So it actually became a little hard to figure out for the TPU hardware, which of these should we weigh more and optimize for, because you might need different kinds of techniques. But by sort of the use of the transformer becoming much more prevalent, you can sort of focus on making transformer models run extremely well as one really important use case, and you end up covering a lot more of the surface area of uses than we did previously.
And that's been a recent decision, right? The all-in on one giant model. That was maybe a 2023 decision?
Around there. Yeah, exactly.
Yeah, I mean, that was the origin of the Pathways project in 2018, was really like we should be training a single unified model that dealt with all modalities. But that's a pretty complicated and long, ambitious agenda, so it took us a while to get there.
So the decision was much earlier, the realization of it, because
Yeah.
I mean, I think at one point we counted, we had, I don't know, 10,000 different models in production.
Wow.
The most of them variants of maybe a parent, but people were optimizing as they would.
If you were to use the same criteria that you came up with the number 10,000, what would you say that is today?
100,
Hundreds.
10,
Yeah, hundreds maybe.
Yeah. I mean, it's still,
But a handful of major ones that
Yeah,
are
exactly.
that are the bulk of the inference traffic, the bulk of the use.
Is the logic there exactly what you were laying out earlier? A bigger model, more data, better results, just applied on steroids? We should just get all the Google products and all the Google usage and all the third-party feeding.
Yeah, I mean, the dream of machine learning is to build models that can generalize to new things they've never seen before. So as you build a bigger model that's seen more things, the likelihood that it can generalize to something new you ask it to do, it becomes much higher. And so that's what you're seeing in the progress of all these models is they've now seen a lot more different kinds of data. They've been reinforcement learning trained on, tasks that people care about that generalize to other tasks people care about. And that's why you now have these single unified models that kind of do all kinds of things.
Well, in that vein, we've been talking a lot about history because obviously Ben and I love history, and it's so fun to relive all this. And but we'd be remiss if we didn't talk about the future, since we have you two here. And maybe to start that, let's talk about bottlenecks. Maybe give us the current state as you guys are working on it today of like what the bottlenecks are to more compute, more performance, and how you see that changing over the next couple of years.
My unfortunate answer to this is everything is a bottleneck. And I'm very certain that if we didn't work on all of them, the one we didn't work on will be the bottleneck that we wish that we worked on. So in other words,
lay them out. What are the?
Energy. It's a significant bottleneck. We've shifted a lot of our work to optimizing performance per watt. Data centers, building these data centers globally across the world. I mean, many issues there, permitting, construction, electricals, mechanicals, et cetera.
Yeah, in many ways, that seems like one of the hardest challenges for Google and your peers right now is just actually standing these things up.
It's a very physical process, very physical process. In other words, we live in the world of photons and bits. This is the world of atoms. I mean, there's a lot of concrete, a lot of dirt, a lot of wires, et cetera. And
Solar panels.
Yeah, solar panels, wind turbines, nuclear reactors, et cetera. So these are bottlenecks. Hardware absolutely is a bottleneck. I mean, and so this is one that people know about. Now it could be wafers from TSMC or others, Samsung, Intel, and others perhaps. It could be memory. It could be PC boards. It could be substrate. So many. But in other words, if I were to pick one,
Could be the rubber widget you need to connect the little cable to this thing.
During COVID, we had, I think, a capacitor that was like 57 cents, like literally from Texas Instruments. By the way, the price of it went to like $500 over some amount of time, and that was the capacitor.
That was the bottleneck.
That was the bottleneck, and we and others, not just us, missed it.
Capacitors are for absorbing charge.
Yeah. Yes. They turn out to be important. So those are bottlenecks. I mean, I think on the software side, we have.
Wait, before we move to software, okay, if number of TPUs is a bottleneck today, if I gave you twice as many dollars and said go build twice as many TPUs and you were able to do that, would it still be bottlenecked?
What would be the bottleneck?
Would TPUs be a bottleneck if we?
Well, let's see. Since we're at the present in 2025, I think we spent 90 billion, 85 billion, whatever the number is in capex. For 26, we've declared about 175 to 185 billion in capex.
We're running your experiment.
So we're running. So I live this daily. My team is responsible for delivering 2x the capacity, 25 to 26, like physically getting it out there in terms of TPUs, GPUs, CPUs, whatever. I think we're going to do it.
Good.
I mean, one thing.
Everything's a bottleneck.
One thing I would say is inference capacity is going to be a growing issue because we see tremendous demand for more tokens in large language model inference. As people start to use more agents in background tasks, those consume more tokens. And low latency, I think, is going to be a really defining characteristic. You see it with V8i. I think making even lower latency.
This is a 5x reduction in latency with T8i?
For the collectives operation, for sure, and the network diameter is smaller. So this is the collectives acceleration engine, which is a special accelerator for the accelerator, actually, that we've built on board. So many different pieces.
Yeah, it's fun. I mean, we were talking about it after the keynote, like Google search, which, Jeff, you lived that, you was obsessed with speed, and that was one of the defining characteristics. Like, search didn't become this ubiquitous product until it passed a certain speed threshold and quality and all that too.
Yeah.
The same thing seems like it's playing out with AI.
I mean, I think we, for the history of Google, have obsessed with the response time of our products, particularly search was like one of the early aspects that we really obsessed over. And we could actually measure the effect of adding latency. So you could take like 0.1% of your users and add 5 milliseconds of latency. And you see they use search less. That's not good. And the contrary is they use search more if it's faster. And so that is something we have like a lot of focus on. And I think you're going to start to see everything in the model latency path, software, better hardware for it, much more focus on that, getting it closer to users for interactive use, which is something that hasn't used to matter a ton for search, because if the data center time is 150 milliseconds and then there's a 150 millisecond round trip to the user, that's a big significant component of that. But with response times for language models initially being more like a second, then like 150 milliseconds doesn't matter as much. But now if you start to bring it down 5x, now you're like, okay, well, I better also have these right next to the user rather than across the country.
My mental model for all these different teams at Google is you get some breakthrough in some area, some team does an amazing job shrinking response time, and then suddenly there's this like giant spotlight.
Giant other bottleneck. Yes. Amdahl's law is a way of normalizing.
No team at Google wants to be the primary bottleneck. And what I always tell all the teams is eventually you're going to be the primary bottleneck. It's going to be your turn.
In the agent world, like what you're seeing is models do some stuff and then they invoke tools. And then they take the output of those tools and then they analyze it and decide what to do next, which might be invoking another tool. If you make the model time go to 0, I think we're going to start to realize that our tools are too slow. Our tools are designed for sort of human cadence interaction in a lot of cases, like list me the files in the directory or like do this SQL query and give me the results. Like that's not very good if your model can do those 100 times faster, make those calls 100 times faster than a human can.
Yeah, it's fun. I remember talking to some friends in the AI world, even just a small number of years ago, and saying like, oh, the AI data centers can be anywhere. It doesn't really matter because like latency is not a thing.
Which is true for training.
Yeah, sure, true for true. But I think even for anything, it was just like, oh yeah,
It's also true for offline inference, and reinforcement learning.
Offline
but that's changing now. Like it sounds like that's going to change.
What are some examples of offline inference?
You want to run some model over every YouTube video that gets uploaded. And so you need to do that, but it's not like a user is waiting for the answer.
A safety classifier.
Yeah. Or you need to like analyze all the web pages that we crawled to do something.
I see.
And there's a fair bit of that kind of inference workload, which is nice because then you want the throughput-oriented chip instead of the inference-oriented chip. Because you don't care as much about latency for that, because it just needs to finish today.
And you can batch them up all the way through.
So then you can use giant batch sizes, which the T is better for than the I.
So T is actually excellent at inference as long as you have a big batch to push through.
Interesting. Right. Have we passed, if we were having this conversation in 2023, and I asked, is more compute going to training or inference? I imagine the answer would be training.
Yes.
Has it flipped?
It is flipping.
Yeah.
It is flipping,
I would say.
Speaking of flipping, we've been talking about bottlenecks, staying in the future. I think, did I see right in the keynote this morning that 75% of code at Google is now written by agents?
So
There's some stat. I don't know if that's right.
It went from 50 last year to 75%.
Yeah,
I think it's probably agents and coding models.
yeah.
yeah, and involved. I mean, I think that, yes.
Yeah. What is the state of coding at Google, and how quickly is it changing?
Jeff.
Yeah, I mean, we actually have been using coding assistants for a long time, and we've seen the stats climb. They went from like 8% one year, and then a few months later, they were at 16% of characters checked into our repository, and then 25%. And now in the last probably 4 months, it's really dramatically shot up because now the models are capable of much longer running tasks, much more complex tasks. So now you can actually say, can you please go write me a module that has this rough high-level English specification? And it will actually go off and do that and write a whole bunch of tests for it. And that would have been, multi-hours of work, or sometimes even multiple days of work. And the models can do that autonomously. And so you're seeing people taking advantage of that because all of a sudden you can, as a software developer, orchestrate a whole bunch of these background tasks to accomplish much more than if you had to sort of give it a 20-minute level of task that might or might not be done correctly.
What will be the last type, when that number is 99% and not 100%, what will be the 1% that humans are still writing?
I think there's a huge leverage in knowing what problem to solve. And I think that's going to be one of the hardest things for these models to really understand is like, what problem should you be working on? And humans just are incredibly good at that selection process.
Well, maybe, this has been amazing, by the way. Thank you both so much. Maybe to bring it home as the last question, you both have lived through incredible tectonic shifts in technology throughout your careers, whether that was the internet or mobile and cloud and everything that came with that. I'm curious to your lived experience today now going through this AI shift. How does it compare?
For me, it's the biggest by far. I mean, I remember seeing, this is a while ago now, NCSA Mosaic, 1993.
Yeah.
Really the first graphical web browser. And I thought, oh my gosh, the world has changed. And the internet exploded. But this is way bigger. If I think about 1993 to when the internet actually changed the world in meaningful ways, it was probably a decade, maybe slightly less. I mean, I remember it was a couple of years ago, I was saying, with this moment in AI, we're going to have a doctor for every patient, a teacher for every student, a cure for every disease. I mean, those are bold predictions. I didn't put a time frame on it, but now it doesn't seem like science fiction. Like, could you imagine that we're going to have a lot of that in the next 5 years? I could. This is the biggest and fastest and likely most impactful thing I've ever seen. I don't know, Jeff.
Is that a law of nature? Will that always be true? In 10 years with whatever's next, is that going to be true again?
The rate of these things, and I haven't, like you all, maybe not quite as well studied. I haven't looking at these things. I mean, if you think Industrial Revolution, electricity, internal combustion engine, you think of the space age, nuclear power, you think of the age of information, all of these are now coming faster and faster and faster with more impact. This is the latest. It's the newest, it's the biggest. So my guess is, I don't know if it'll be 10 years, but sometime in the next 10 to 20 years, we're going to have the next thing.
Yeah,
That's even bigger.
I think this is a really big deal, bigger than any of the previous kind of things you mentioned. And the reason is it applies to so many things, right? Like all the huge societally beneficial things we could do with AI, like much better healthcare, education for everyone, the ability to accelerate science itself is going to be huge, especially if you can get automated experiments with a human not in the loop to really like explore complicated spaces of different domains of science. that's going to be amazing, and it's going to lead to new breakthroughs and new things that may not be as broadly applicable as AI, but AI is going to drive those kinds of things. And it's up to all of us to make sure that we push on those aspects of AI that are going to be most beneficial to everyone. And we really also recognize that there are some aspects of AI that are maybe not so positive, and we work collectively to, eliminate or reduce those aspects. And I think that's something that everyone should take to heart.
What I can predict with confidence, though, as an infrastructure person, is no matter what, it's going to take a lot of compute power.
Yeah.
A lot of
There's always going to be a bottleneck.
I think specialization is going to be a bigger deal.
Yeah, specialization will be a bigger deal, absolutely.
Hardware specialization.
Yeah.
Well, that feels like the perfect place to leave it, given where we are today, and with our friends on the table here.
Yes.
Congratulations again to both of you guys. Let's give our guests a hand.